Welcome to this coding walkthrough. Today, we'll dive into problem number 1102, titled Path with Maximum Minimum Value. We'll explore an interesting problem-solving approach to navigate through a grid while maximizing the minimum value along the path. Let's get started. In this problem, we are given an mxn integer matrix called grid. A path in this matrix is defined as a sequence of adjacent cells, where adjacency means the cells share an edge, such as up, down, left, or right. The goal is to find a path that starts at the top left corner of the grid, which is at position 0, 0, and ends at the bottom right corner, located at M1, N1. Along this path, we calculate the minimum value, which is the smallest value among all the cells in the path. Our objective is to maximize this minimum value over all possible paths. In simpler terms, we need to find the path where the smallest number encountered along the way is as large as possible. The input is the grid itself, and the output is a single integer representing this maximum minimum value. For example, consider the grid 5, 4, 5, 1, 2, 6, 7, 4, 6. The output for this input is 4. The reasoning is that the path that maximizes the minimum value starts at 5, moves through 4, then 5, 6, and finally 6. The smallest value along this path is 4, which is the maximum possible minimum value for any path in this grid. No other path can achieve a higher minimum value. This illustrates the essence of the problem, finding a path that balances movement across the grid while keeping the smallest value as high as possible. Now, let's look at another example. Consider the grid 2, 2, 1, 2, 2, 2, 1, 2, 2, 2, 1, 2, 2, 1, 2, 2, 1, 2, 2, 2, 2, 2, 1, 2. The output for this grid is 2. In this case, the path that maximizes the minimum value consists of all 2s, which ensures that the smallest value in the path remains 2. Even though there are other possible paths, none of them can achieve a minimum value greater than 2. This demonstrates how the algorithm must carefully choose paths to maintain the highest possible minimum value. Next, take the grid 3, 4, 6, 3, 4, 0, 2, 1, 1, 7, 8, 8, 3, 2, 7, 3, 2, 4, 9, 8, 4, 1, 2, 0, 0, 4, 6, 5, 4, 3. The output here is 3. The path that achieves this result starts at 3, then moves through 4, 6, 3, 7, 7, 8, and finally 3. The smallest value along this path is 3, and no other path can achieve a higher minimum value. This example highlights how the solution must navigate a complex grid, balancing movement and value selection to maximize the minimum value. Lastly, let's consider some edge cases and constraints. For a single-cell grid, the output is simply the value of that cell, since there's only one possible path. For example, if the grid is 5, the output is 5. If all values in the grid are the same, such as 1, 1, 1, 1, the output is the common value, in this case 1. The algorithm must also handle large grids, up to 100 by 100 in size, with values as high as 10 to the power of 9, efficiently. Additionally, when high-value cells are sparse, the solution must avoid greedily choosing a high-value path that leads to a lower minimum value later. These cases emphasize the importance of designing an approach that carefully balances exploration and computation to ensure optimal results in all scenarios. To solve the problem of finding the path with the maximum minimum value, the most straightforward approach to consider is brute force. The intuition behind this method is to explore all possible paths from the top left to the bottom right corner of the grid. For each path, we compute the smallest value along that path, and then track the maximum of these minimum values across all paths. This guarantees that we find the result, as we're evaluating every possibility exhaustively. However, there are some important observations to note. A path can be represented as a sequence of moves in the grid, such as up, down, left, or right. While the idea is conceptually simple, the major limitation is the computational cost. The number of paths grows exponentially with the grid size, making this approach infeasible for larger grids. In terms of complexity, the time required is exponential due to the sheer number of paths we need to evaluate. The space complexity, if implemented using recursion with depth-first search, would be proportional to the size of the grid. This approach is impractical and therefore not chosen for this problem. Instead of evaluating all possible paths, we can use a more efficient method that combines binary search with BFS or DFS. The intuition here is to transform the problem into a decision problem. Instead of directly calculating paths, we ask, is there a path where all values are at least a certain threshold, mid? To achieve this, we define our search space as the range of values in the grid, from the minimum value to the maximum value. Then, for each midpoint mid in this range, we use BFS or DFS to check if a valid path exists where every value along the path is at least mid. If such a path exists, it means we can adjust our binary search bounds to potentially find a larger minimum value. Some key observations make this approach viable. First, since the grid values are finite, binary search is a natural fit. Second, BFS or DFS allows us to efficiently verify the feasibility of paths for a given mid. The complexity of this method is significantly better than brute force. The binary search requires O, log, max, min, iterations, and for each iteration, BFS or DFS takes O, m*n, time, resulting in an overall time complexity of O, log, max, min, *m*n. The space complexity is dominated by the BFS or DFS, which requires O, m*n, space. While this is a significant improvement over brute force, there's an even more optimal approach that we can use. A highly efficient method to solve this problem uses a max heap, or priority queue, to greedily find the path with the maximum minimum value. The intuition here is to leverage the priority queue to always prioritize paths with the largest values first, ensuring that we explore the most promising paths early. We start from the top left corner of the grid and initialize a max heap with its value. At each step, we pop the cell with the largest value from the heap. For each of its unvisited neighbors, we calculate the new path minimum, which is the smaller of the current path minimum and the neighbor's value. This neighbor is then pushed into the heap with the updated path minimum, and we mark it as visited to avoid revisiting it. This process continues until we reach the bottom right corner of the grid. A key observation here is that the max heap ensures we always process paths with higher minimum values first. This greedy strategy guarantees that the first time we reach the bottom right corner, the solution is optimal. The time complexity of this approach is O, m*n*, log, m*n, where the log factor comes from heap operations. Space complexity is also O, m*n, to account for the heap and the visited set. This approach is efficient and directly aligned with the problem's requirements, which is why it's the most suitable choice. The chosen strategy for this problem is the max heap or priority queue approach. This method is both time efficient and intuitive, directly addressing the problem's goal of finding the path with the maximum minimum value. Unlike the brute force method, it avoids the computational expense of exploring every possible path. Compared to the binary search approach, it eliminates the need for iterative feasibility checks by directly prioritizing the most promising paths as we progress. The greedy nature of the priority queue ensures that we always move towards the optimal solution, and the use of a max heap allows us to efficiently manage and explore the grid. This combination of efficiency and simplicity makes the max heap approach the best strategy for solving this problem. The problem challenges us to find a path through a grid where the smallest value encountered on the path is as large as possible. We can only move right or down, starting at the top left corner and reaching the bottom right corner. To better understand, imagine traversing the grid and evaluating each path based on its smallest number. Our goal is to maximize the smallest value across all possible paths. One way to solve this is by exploring all potential paths, which we can do using recursion. Starting at the top left corner, we recursively move right or down, keeping track of the smallest value encountered along the way. If we reach the bottom right corner, we return that path's minimum value. This approach ensures we calculate the smallest value for every possible path. However, we must account for a base case. If we're already at the bottom right corner, we return the minimum value for the current path immediately, as no further moves are possible. After calculating the minimum value for all possible paths, we then find the maximum among these minimum values to determine the optimal path. This represents the best path based on the problem's constraints. To improve efficiency, we can implement memoization. By storing results of previously solved subproblems, we avoid redundant calculations, which is especially useful for overlapping subproblems. However, the brute force approach still has significant computational limitations. The total number of paths through the grid is determined by the formula m plus n2 slash m1 asterisk n1, which grows exponentially with the grid size. This makes it clear that exploring all paths without optimization is impractical for large grids. A key takeaway is that the quality of a path is defined by its smallest value, which we aim to maximize. While recursion provides a way to break the problem into smaller subproblems, it becomes inefficient without techniques like memoization. To optimize further, we can use a memoization table. This table stores the maximum-minimum value for every path starting at a given cell, allowing us to reuse previously computed results. For example, if memo I(j) contains the result for cell I(j), we can directly use it instead of recalculating. Let's walk through an example to see how this works. Consider the grid 5, 1, 7, 2, 6, 8, 3, 4, 9. Starting at 0, 0, the initial minimum value is 5. From here, we can move right to 0, 1, where the new minimum becomes min 5, 1 equals 1, or move down to 1, 0, where the new minimum becomes min 5, 2 equals 2. This process continues recursively until reaching the bottom right corner. By keeping track of the minimum value encountered along each path, we can evaluate the quality of the path as we go. At the end of the recursive exploration, we calculate the minimum value for each path. For instance, in our example grid, one possible path is 0, 0, 0, 1, 0, 2, 1, 2, 2, 2, which has a minimum value of 1. Another path, 0, 0, 1, 0, 1, 1, 2, 1, 2, 2, has a minimum value of 4. A third path, 0, 0, 1, 0, 2, 0, 2, 1, 2, 2, has a minimum value of 3. Out of these, the maximum minimum value is 4, which becomes our result. The brute force approach has a time complexity of O(2) m plus n, due to the exponential growth of paths, but with memoization, this can be reduced to O(m n). The space complexity includes the recursive stack, which is O(m plus n), and the memoization table, which requires O(m n) space. This optimization makes the problem tractable for larger grids. To solve the problem of finding the path with the maximum minimum value in a grid, we begin by importing the necessary library heap for working with a priority queue, or heap. The function maximum minimum path is defined within the solution class, and our input is a 2D grid. First, we determine the dimensions of the grid, rows and calls, and define possible movement directions as 0, 1, 1, 0, 0, -1, -1, 0, to represent moving right, down, left, and up. Next, we initialize a min heap, which stores tuples in the form value, row, call. Using negative values allows us to simulate a max heap behavior, ensuring we always prioritize the largest minimum value at each step. We push the starting cell, which is the top left corner of the grid, onto the heap with its negative value. We also initialize a visited matrix to track cells we've already processed, marking the starting cell as visited. The variable max_min_value is initialized to the value at the top left corner, which is our starting point. Now, we enter a while loop that continues until the heap is empty. At each iteration, we pop the cell with the current maximum-minimum value from the heap. The max_min_value is updated as the minimum of its current value and the value of the cell we just popped. If the current cell is the bottom right corner of the grid, we return max_min_value as the final result. Next, we focus on exploring the neighbors of the current cell. For each possible direction, we calculate the coordinates of the neighboring cell, NX and New York. We ensure the neighbor is within the bounds of the grid and has not been visited yet. If these conditions are met, we mark the neighbor as visited to avoid processing it multiple times, and we push its value onto the heap as a negative value along with its coordinates. This ensures that higher values are prioritized in subsequent iterations of the loop. After exhausting all possible moves, the loop will eventually terminate when we reach the bottom right corner, returning the maximum minimum value of the path. As a fallback, The function includes a return value of -1, although this case should never be reached under the given problem constraints where a path is always guaranteed to exist. Here, we are implementing the solution for the path with maximum minimum value problem in Java. We start by importing necessary utilities and defining the solution class. Inside the maximum minimum path method, we take a 2D grid as input and calculate the number of rows and columns. We then define the 4 possible movement directions: right, down, left, and up, using a directions array. To help us efficiently find the optimal path, we use a priority queue, implemented as a max heap. Since Java's priority queue is by default a min heap, we simulate a max heap by storing negative values and define a custom comparator to prioritize larger values. The priority queue initially contains the starting cell at the top left corner, represented by its value, row, and column indices. Next, we create a Boolean matrix visited to track which cells have already been processed and mark the starting cell as visited. We also initialize max-min value to the value of the starting cell, as this will keep track of the smallest value encountered along the path. The while loop begins, which will continue until the priority queue is empty. In each iteration, we extract the cell with the highest value using poll, and then update max-min value to the smaller of its current value and the value of the extracted cell. This ensures that we are maintaining the maximum of the minimum values encountered so far. If the current cell is the bottom right corner of the grid, we return max-min value, as this signifies the end of our path with the desired result. If we have not yet reached the bottom right corner, we proceed to explore all valid neighbors of the current cell. For each direction in the directions array, we calculate the potential new coordinates, NX and New York. We check if these coordinates are within the grid bounds and whether the cell has not already been visited. If both conditions are met, we mark the neighbor as visited and add it to the priority queue. The value of the cell, along with its coordinates, is added as an entry in the max heap to ensure it is processed in order of priority based on its value. This process continues until we either reach the bottom right corner or exhaust all possible paths. If the bottom right corner is reached during this process, the method immediately returns max-min value, which represents the maximum minimum value along the path. However, to handle edge cases where no path exists, although this should not occur given valid inputs, we return -1 at the end of the method as a fallback. This completes the implementation, ensuring that we efficiently calculate the maximum minimum value in the grid using a combination of priority queues and a breadth-first search approach. Here, we begin with an example grid of size 3 by 3. The dimensions of the grid are noted as 3 rows and 3 columns. To navigate through the grid, we define the 4 possible movement directions: right, down, left, and up. Next, we initialize a min heap starting with the negative of the top left corner value, which is -5, to simulate a max heap behavior. We also set up a visited matrix to track the cells we've already explored, marking the top left corner as visited. The variable max_min_ value is initialized to the value at the top left corner, which is 5. During the first iteration, we pop the top element from the heap, which is -5 at coordinates 0, 0. We update the max_min_ value to the minimum of its current value and the absolute value of the popped element, which remains 5. Then, we explore the neighboring cells. Moving to the right, we push -4 from 0, 1 to the heap and mark it as visited. Moving downward, we push -6 from 1, 0 to the heap and mark it as visited. Now, the heap contains -6 and -4, corresponding to the cells 1, 0, and 0, 1, respectively. The updated visited matrix reflects these newly visited cells. In the second iteration, we pop the top of the heap, which is -6 from coordinates 1, 0. The absolute value of -6 is 6, but the max_min_ value remains 5 since it is the minimum of 5 and 6. We then explore the neighbors of 1, 0. Moving to the right, we push -1 from 1, 1 to the heap and mark it as visited. Moving downward, we push -7 from 2, 0 to the heap and mark it as visited. At this point, the heap now contains -7, -4, and -1, and the visited matrix is updated accordingly. As we continue, we repeatedly pop from the heap, updating the max_min_ value on each step, and exploring valid neighbors. This process proceeds until we reach the bottom right corner of the grid at 2, 2. The final path taken is 0, 0, 1, 0, 2, 0, 2, 1, 2, 2. Throughout this path, the minimum value encountered was 5, so the result for this grid is 5. Moving on to a new example, we now consider a grid where the top left corner value is 1. The heap is initialized with -1, and the visited matrix marks the top left corner as visited. The max_min_ value is set to 1, the value at the starting point. In this new example, we begin by popping the top of the heap, which is -1 at coordinates 0, 0. The absolute value is 1, and the max_min_ value remains 1 as it is the minimum of 1 and 1. Exploring the neighbors, we move to the right and push -2 from 0, 1 to the heap, marking it as visited. Moving downward, we push -4 from 1, 0 to the heap, marking it as visited as well. The heap now contains -4 and -2, and the visited matrix shows these cells as visited. Progressing through the grid, we continue to pop cells from the heap, updating the max_min_ value and adding valid neighbors to the heap. The final path taken is 0, 0, 1, 0, 2, 0, 2, 1, 2, 2. The smallest value along this path is 1, so the result for this grid is 1. In the third example, we start with a smaller grid where the top left corner value is 10. The heap is initialized with -10, and the visited matrix marks the top left corner as visited. The max_min_ value is set to 10. During the first iteration, we pop the top of the heap, which is -10 at coordinates 0, 0. The absolute value is 10, and the max_min_ value remains 10. Exploring the neighbors, we move to the right and push -10 from 0, 1 to the heap, marking it as visited. Moving downward, we push -10 from 1, 0 to the heap, marking it as visited as well. The heap now contains -10 and -10, representing the cells 0, 1, and 1, 0. As we proceed through this grid, the path eventually reaches the bottom right corner at 1, 1. The smallest value encountered along this path is 1, so the result for this grid is 1. This concludes the solution walkthrough, demonstrating the process of finding the path with the maximum minimum value across multiple examples. The time complexity of this algorithm is primarily determined by two major components: heap operations and neighbor exploration. First, let's consider the heap operations. The algorithm uses a min heap to store and retrieve cells based on their values, which are negated to simulate max-min behavior. Each push or pop operation on the heap takes O log k, where k is the current size of the heap. In the worst case, every single cell in the grid is pushed into the heap exactly once. For a grid of size rows x calls, the total number of cells is n, which equals rows multiplied by cols. This means there are O, n, heap operations overall, and since each operation costs O log n, the total contribution of heap operations to the time complexity is O, n * log n. Next, we examine neighbor exploration. Each cell in the grid has up to 4 neighbors, and since each cell is visited exactly one time, the total number of neighbor explorations is proportional to the total number of cells, or O, n. These neighbor checks are constant time operations, so this step contributes O, n, to the time complexity. When we combine the heap operations with neighbor exploration, the overall time complexity of the algorithm becomes O, n * log n, where n is the total number of cells in the grid. Now, let's focus on the space complexity of the algorithm. The space usage can be divided into 3 main components: the heap, the visited array, and a small set of variables. First, the heap is used to store at most n elements, where n is the total number of cells in the grid. Each element in the heap is a tuple containing 3 items, the negated value of the cell, and the cell's row and column indices. Since each tuple requires O1 space, the heap as a whole requires O(n) space in the worst case. Second, the visited array is a 2D Boolean array that tracks whether each cell in the grid has been processed. Its size is proportional to the grid size, requiring O rows * calls space, which simplifies to O(n). Finally, there are a few additional variables such as max_min_ value and the list of movement directions, all of which require only constant space, or O1. these contribute a negligible amount to the overall space complexity. When we combine the heap and the visited array, the total space complexity of the algorithm is O(n), where n is the number of cells in the grid. To understand the efficiency of this approach, let's compare it to the brute force method. A naive brute force solution would involve generating all possible paths from the top left to the bottom right corner of the grid. For each path, we would calculate the minimum value along the path and then return the maximum of these minimum values. However, the number of paths in an mxn grid grows exponentially, with a worst-case time complexity of O(2)m plus n. Evaluating all these paths would add even more computational overhead, making this approach infeasible for large grids. In contrast, the optimized solution uses a greedy strategy combined with a heap to explore paths efficiently. By focusing on maximizing the minimum value at each step, this approach avoids the exponential blowup of the brute force method. Instead, it achieves a significantly better time complexity of O(n*log n, where n is the total number of cells in the grid. This makes the optimized approach much more scalable for practical use. Let's break down the performance of the algorithm under different scenarios. In the best case, the grid is small, and the algorithm quickly identifies the optimal path. While the time complexity remains O(n*log n, the actual runtime is reduced because there are fewer heap operations. In an average case scenario, such as a typical grid, the algorithm explores most of the cells, so the runtime is close to O(n*log n. Finally, in the worst case, the algorithm must explore every single cell in the grid and perform heap operations for each one. Even in this scenario, the time complexity is still bounded by O(n*log n. To support this analysis, we can look at the mathematical proof for the big O complexity. Each heap operation, whether it's an insertion or deletion, takes O log k, where k is the size of the heap, which is at most n. With a total of n heap operations, this contributes O(n*log n. Additionally, neighbor exploration involves visiting each cell once and performing constant time checks for up to 4 neighbors, which contributes O(n). When we combine the contributions from heap operations and neighbor exploration, the overall time complexity of the algorithm becomes O(n*log n plus O(n). Since O(n*log n dominates O(n), we simplify the expression to O(n*log n. This final bound captures the efficiency of the algorithm and highlights its scalability for large grids. By utilizing a heap and a greedy approach, the algorithm ensures that operations are performed as efficiently as possible while maintaining correctness. One of the most common pitfalls in solving this problem is misunderstanding the requirements. For instance, not paying close attention to whether diagonal moves are allowed or whether the grid contains obstacles can lead to designing a solution that doesn't meet the problem's constraints. It's crucial to clarify these details and think through edge cases before diving into the implementation. Another frequent issue is relying on an inefficient brute force approach, which attempts to explore every possible path without any optimization. This is especially problematic in larger grids, as the number of potential paths grows exponentially. Before coding, it's important to carefully analyze the time complexity to ensure feasibility. Additionally, edge case scenarios, such as grids with only one row or column, grids filled entirely with obstacles, or cases where the start or end cell is inaccessible, are often overlooked. Ignoring these can cause runtime errors, so they should be considered upfront. For recursive solutions, failing to use memoization can dramatically increase runtime due to redundant calculations. By caching results for overlapping subproblems, you can significantly improve performance. Lastly, boundary checks are another tricky area. When navigating the grid, it's easy to accidentally access out-of-bound indices, so handling boundary conditions with care is essential to avoid index errors and ensure correctness. Now, when preparing for interviews, it's important to remember that interviewers often expect you to start with a brute force solution but eventually optimize it. Problems involving grids are particularly well suited for dynamic programming, and you should be ready to explain how your approach balances time and space complexity. One helpful strategy is to look for patterns shared by many grid-based problems, like solving subproblems by combining results from adjacent cells. Recognizing these patterns can help you quickly derive a recursive or dynamic programming relationship. Another critical aspect is handling edge cases. Interviewers frequently ask about these, so proactively discussing how your solution addresses them demonstrates thoroughness and foresight. Additionally, you should be prepared to explain why you chose an iterative or recursive approach. While recursion can be more intuitive, iterative solutions are often preferred in interviews due to their better space efficiency. Lastly, practicing related problems can strengthen your understanding. For example, LeetCode 64 focuses on finding the minimum path sum, while LeetCode 62 and 63 deal with unique paths, including scenarios with obstacles. LeetCode 174, the dungeon game, is another great example that requires careful handling of grid traversal and optimization. There are also several alternative approaches to solving this type of problem, each with its own strengths and trade-offs. First, dynamic programming with a bottom-up approach uses a 2D table to store results for each cell, ensuring optimal substructure. This method has a time complexity of O, n asterisk m, and you can even reduce the space complexity to O, min, n, m, by using a rolling array. Another option is a top-down recursive approach with memoization. This leverages recursion and a memoization table to store previously computed results. While this approach is more intuitive, it does require additional stack space and can run into stack overflow issues for very large grids. For problems that involve finding the shortest path, breadth first search, or BFS, can be an effective alternative. BFS guarantees that the first solution found is optimal, but it typically requires more memory compared to dynamic programming. Finally, for pathfinding problems where grid cells have weights, algorithms like Dijkstra's or A** can be used. These are well suited for more complex scenarios and provide a structured way to find the optimal path based on weighted costs. Great job making it to the end. To summarize, we tackled the problem path with maximum minimum value with an efficient approach. Along the way, we learned about grid-based pathfinding and techniques like binary search and greedy algorithms. Thanks for watching, and be sure to like, subscribe, and share for more problem-solving tips. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!